Sahus are asking you to join or something. I mean, that may be some reason for some people, right? Some of you I can see smiling. I think that was the reason. That's okay. But I'm sure there is other reasons as well, right? So uh, anybody wants to volunteer? Any questions that you want to discuss? Any challenges? Go ahead. Okay, that's a very good question. So railroad design does not really have like a design life like that. So because if you think about it, it's not really a fatigue based design or anything. It's a material decomposition based design, and you don't really have, you know, exact uh, design life per se. What they do is they try to limit the stress levels at different to different values. That is how the design is done. A lot of it is actually based on very old methods. Uh, and after that, one unique thing about railroads, at least in North America and Europe, is the inspection is very regular, extremely regular. I mean, you'll be surprised by the technology that gets used to regularly track it, and that is the reason is because the stakes are very high. The moment you have a derailment, you're talking millions and millions of dollars and people dying and all of that right stuff. So it gets uh, evaluated, and then depending on the track location, they can have what is known as, so the ballast, it can have different things. So ballast undergoes what is known as fouling. I told you, right? Fouling is dirty basically, and degradation is one of the primary mechanisms. Like when ballast churns against each other, it gets fouled and stuff. So they have something called edge cleaning, shoulder cleaning, where what happens is uh, the way railroad tracks work is, and it's a very interesting problem as well. So if anybody wants to go into some really deep analysis and stuff, this is kind of how a typical railroad track looks. I mean, the track lies here, right? So the rails are going that way and stuff, right? So when it rains, and this is all ballast and stuff, so they have a shoulder, they have certain specifications how to do shoulders. I'm sure Indian specifications have that as well. The problem is when you have your cross ties here, this is a tie, let's just say, right? And then you have ballast all over here, and then it rains, or it starts getting fouled. So there is a lot of areas here that are fouled. Then it rains, right? The water actually washes the fines towards the shoulders, right? So it actually gets here and here. So with time, you'll see the ditch or the shoulder area getting really dirty and everything, and that actually prevents free flowing. So what they do is they come and they do what is known as shoulder cleaning. They actually have an excavator kind of thing. They actually dig like a trench. They pick up the material, they run it through a sieve shaker, reject all fines, and the big material they put it back and stuff. And depending on the site, that can happen once a year, once in 6 months, once in 3 months, once in 4 months and stuff. I mean, it all depends on how bad a site is, right? And resurfacing, like, you know, when they have a deformation, like, you know, they have the track profile going out of geometry and stuff. In busy corridors in America, like the Northeast corridor where it's very passenger heavy and stuff, they actually do the inspection every 2 weeks. Every 15 days they have a detailed inspection, and if there is a problem, they come back and fix it. So the site I was showing that we were working, they actually had to come back and fix it every month once, and that is why we fixed it, and it was able to be pushed to at least once in 2 years and once in 2.5 years and stuff, which ended up being really nice. So there is not real design life per se, but it's site dependent. It's not unheard of for them to come and address something every month if it's a very critical site and it's having a lot of problems and stuff. No, I mean they are, yes, but 95% to 96% of the ties are still of wood or timber ties. If you take the total track mileage in US, about 5% or 6% are concrete. Rest are timber still. Timber has certain advantages. There is an abundance of wood, and it also has some advantages because it's it's more absorbing. It's not as rigid. It doesn't degrade the ballast very bad. But when you go to higher speed, higher demand, like Northeast Corridor, which is where Amtrak runs a lot of the passenger, there is a lot of uh, concrete ties, concrete truss ties, but a lot of timber as well. Anybody else? Yes, Atanu. Okay. Binder. Uh-huh. I'm not an expert in anything. I'm just somebody who works. I don't call myself an expert in anything except movies. I know a lot about movies. If you want to talk about movies, we can talk. Go ahead. So modulus. So all I can say is I have done FWD work on cold in place recycling, cold mixes and stuff, and some modeling, some FWD and stuff. I have not tested them for resilient modulus, but the modulus we used was 100,000 psi. If you want just one E value, so it's about 100. So a typical good quality aggregate was about 40. As I showed, 40, 45 is a very good quality aggregate. We used about 100, 80 to 100. That's all I can say. I've not tested it in myself, but that's the FWD and the run triaxial testing, fit a K theta model, see if what do you mean by triaxial, like resilient modulus, or okay, and it is pressure dependent, then it is pressure dependent. I mean, it is what data says, right? I mean, it is yeah. I mean, you can. Are you able to run a shear strength test? Can you apply confining pressure and shear it? Is your device strong enough to shear that material, or is it too strong? Right. I mean, if you do I mean, you have seen resilient modulus, but if you do like a triaxial and you actually are able to plot a more Coulomb like this, then it answers everything. That it's a frictional material for sure. Try that. Try three different confining pressure. At least two different confining pressure. Do you see a difference in shear strength? That will work. Anybody else? Come on, guys. We have to talk till 1 o'clock. Otherwise, Sahu sir will not give me lunch today. Okay, we can take a look at GeoTrack if you want. So I think I should do this. Okay, so oh, what? So this is the original paper for GeoTrack. I will share it with you all. Uh, it's again a layered elastic program. It was developed by Professor Ernie Seelig, who is no more, but he was a professor at University of Massachusetts, and the whole idea of GeoTrack is that it is a beam that is districtly supported uh, dis, by the ties basically, and it's a BOEF, beam on elastic foundation model basically, but the way the loads are transmitted is that you take the loads Q1, Q2, these are the two wheels on the two rails, and then you are dividing the tie into 10 little circles. Okay, the tie ballast or the sleeper ballast interface is divided into 10 different circles, and those circles is where the pressure is applied. And if you look at one circle, it's nothing but a tire applying a load on a pavement, right? So beyond that, it just becomes a problem of superposition and stuff, right? So then you have, it's a 11 tie section where they actually model the force going into the track and stuff, and that's basically the shape, three-dimensional multi-layer model, elastic response, components are shown. Rails are represented by linear elastic beams supported by a number of concentrated reactions, one at each intersection. The rail spans 11 ties and are free to rotate, and then the connection between rail and tie is represented by a linear spring, which is given some constant. Ties are represented as linear elastic beams specified by modulus of elasticity, and then the ties are supported by the underlying layer. And this is some some mathematics underneath there. Again, go back to your beam theory and stuff. This is some of my hand notes and stuff, and it can actually do some hysteresis behavior, some stress dependent behavior and stuff like that. So back in 2015 or 2014, when I started as a faculty at Boise State, we talked to this Association of American Railroads. They had very interesting problem. They had an executable version, like a DOS executable version of GeoTrack, for which they didn't have a source code, and they had a source code which would not compile, so they did not know which one was it for. So it was not for the executable version. So they basically gave me and said that, okay, figure this out, check this code if it is correct or not, recompile this, fix this and stuff. So that was my first master student who did all of this work, and we developed this GeoTrack code that I'm going to show you right now. And we can show you what I think. Sahusar is not here right now, but I think there is a good need for something like this for India, and you all people who are pursuing research and stuff, you should think about it, because beam on elastic foundation is something that pavement community has really been an expert in. So just do something with it. So what my student did is, she was again a champion programmer, and what she did is she made this into a GUI completely. So this is the GeoTrack GUI. I'm going to launch it, and as I said, I cannot share this with you. I would love to, but I am not allowed to, because this is a private company. They sponsored this, so it's their IP. They have in fact told me if I give it publicly, I may face lawsuits and stuff. So of course I'm not going to do that. So what you can do is you can either input material properties manually, or we'll do something that's much easier. I'm just going to go, no, this is an input file, and we're going to take a look at this together and see what's going on. So this is a layer. There is 5 layers. The modulus is 40,000, 20,000, 4988, 4350, and whatnot. The modulus, the Poisson's ratio values, how deep are they, what is the unit weight, what is the K naught value, and what is K1, K2, K3. These are stress dependent parameters. Then you go to rail properties. You can actually define rail properties, like, these are some predefined rail sections with defined properties. And folks who are doing masters, if you want to do a thesis and stuff, remember this was done by a master student for her thesis. This is not PhD work. This is a master student developed the entire code from scratch. She had no clue what railroad was, and then she started, and in 2 years, less than 2 years, she did this. Then tie, there is other, there is concrete, there is wood, you have different things. And then load, how many axles are you applying? This is 3 axles basically, because that actually usually represents the stretch. Then it says first tie, where it is located, last tie, first segment, last segment. That's basically some parameters in terms of where load should be applied. So then you can actually just do run analysis, and it's just going to go. I'm going to just save it as again. Save. Oh my God, what the heck just happened? I just ran it right now. File open. Okay, good. Thank God. I think I did something previously wrong. So what it does, folks, is it plots by default some plots, which basically is tie number versus rail and tie deflection. So where the load is and how the ties are deflecting, and because of the location of the loads. Tie number versus tie bending moment. So now you can track the bending moment of individual ties, because that's actually a failure criteria. Tie number versus rail bending moment, and then rail seat reaction. This is what I showed you about the strain gauges and stuff, like how much force is being transmitted and stuff like that, right? But not only that, what you can do is we develop this open-ended plotting window, where you basically say what tie are you interested in. Okay, I'm interested in tie number 1. What segment? Remember, every tie has 10 segments, and we divide it into 5 because it's axisymmetric, like half of it. And then you select all the segment, and what kind of plots. This is vertical displacement. So now it is plotting the segment numbers, where each the segment is. Segment number 1 is under the rail, so of course that has the highest deformation. As we go away, it's in the middle of the track and stuff. So that's how it is doing less and stuff. And then you can change this to bulk stress, where the bulk stresses are high, of course under segment number 1, because it's under the rail. Imagine how a load is transmitted, right? If you think about it, this is actually a very interesting problem in railroads as well. If you look at the cross section, this is the rail, and there is a tie underneath here, right? So the loads are coming through this and then going like that and like that. So the question is, when you design a tie, do you really need the same thickness in the middle? You don't, right? Because there is nothing happening here. So that's the reason tie designs are usually like this. Ah, I ran out of space. That's how ties are designed basically. Because the middle thickness, you don't need it. It's thinner. There is no load transmission happening. It's beam, right? Save material and stuff like that. So that's what's happening here. The bulk stresses are also higher because segment number 1 is actually here. So it's actually somewhere. Yeah. And then you divide that into segments going into, and 5 is kind of in the middle and stuff like that. So that's bulk stress. You can do maximum principal stresses, you can do minimum principal stresses and all of that. So this is just running the layered elastic analysis, and you can give all the output and everything to run this. It's nothing rocket science, but it's very useful tool to do that. So this is what we developed for them. We gave it to them, and they didn't. Original plan was for us to develop an official GUI for them, but then they got into because they are a company, they have software design standards, like, this is how software should be, and I'm not an IT person, so we just handed it over to them. And then you can do a lot of other things. You can actually do something like, query track response. It's saying that, okay, what do you want? So I'm going to say, what happens on tie number 1 at a depth of 12 inches, less length from first into tie number 1 at a depth of, let's just say, 6 inches from the set, and then you just query. It actually gives you the stresses and strains, like what is the vertical deformation, what is the bulk stress, what is the vertical principal stress, and everything. So just like GeoTrack did yesterday, right? You could do Illipave did yesterday with the query points and stuff. You're doing the exact same thing here. That's one aspect. The other aspect you have is you can do permanent deformation calculation. So basically what you can do is QU just based on the SSR stuff, unconfined compressive strength versus vertical stress. You can actually mention a QU, Q50 or something, and then calculate. It will actually give you sigma D. It will actually give you permanent deformation is 0 here. I don't know what happened. 20. It's been a long time since I played with this. So this was, it's not a number, maybe because it's the classifications. It's probably too small. I don't know. I don't remember exactly what the deal is, but there is. Oh, sorry. I'm so sorry, guys. Yes. In minus infinity plus infinity. Wow. 1000 load reputations. QU. I don't know why it's doing that. Okay, I'm not going to waste time. The other thing you can do here is run dynamic analysis, which is basically in GeoTrack, or not in GeoTrack. In the original GeoTrack, this was not there. In ARIMA, what they do is they say that, static. This is all quasi-static, right? Static analysis. They say that a rail, based on its diameter and based on the speed, applies certain amount of dynamic loading for this. There is a fixed formula. It's not It's not something, you're not doing true dynamics or anything. There's a fixed formula to translate that, so you can actually do that. Wheel diameter, if you just say, I don't know, 24 inches, and vertical speed is 45 miles per hour. If you do run dynamic analysis, then it actually can plot you figures or anything for the dynamic case. Now under it enhances the load that you are applying. It just multiplies that by a factor and then does that. Okay, and what is this used for? I'm going to show you something very quickly, and that's pretty much going to be all I'm going to do today. Give me one. Oh no, not here, sorry. This is the importance why you do this. I'm going to show this to you quickly. This is another ongoing project. So the whole idea is why you need this is because track conditions are non-uniform, superstructure and substructure get degraded, and performance is influenced by the degradation of superstructure, substructure, and we need to frequently monitor that. And one of the factors that you monitor this is something called track modulus. Okay, in pavements you did not hear something called pavement modulus. You heard about individual layer modulus. Here also that exists, individual layer modulus, but you also represent something called track modulus, the overall load deformation behavior of the entire track, and I'll show you the equation for that. And modulus is an indicator of the quality of the track. And in the US, I mean, this is a project I currently have with the Department of Defense or the Army Corps of Engineers, because they have certain maintenance standards. They say that if you have 5 ties that are bad consecutively, then that track is bad. That's just an empirical, previously experience wise and stuff. So they actually contacted us saying that, what is the meaning of these 5 ties? Is 5 ties actually bad, or can it be made 7, or should it be made 3, right? What is the impact of all of these on track modulus? How does the stress strain dissipate or load distribution happens and stuff like that? So that's basically our project. So our questions is, what is the effect of support conditions underneath a tie on track's load deflection behavior? What is the effect of a weak zone under certain ties? What is the variation in properties of weak zone? And how sensitive is track modulus to variations in different substructure properties? So if you have a track with certain modulus, now your subgrade changes. Is that having a big effect on the modulus? Or ballast change, does it have a big effect on the modulus? Because that's how it's indicating the overall structural health of the track. So in this one, what we have done is the theory behind track modulus. How does it represent track conditions? What factors influence track modulus? What are the traditional measurement approaches? What parametric numerical studies have been conducted? What are the measurement systems and stuff like that? So this is the theory. Okay, this is theory. If you look at it, track stiffness, very first class I told you this, stiffness versus modulus. And somebody actually, I think yesterday or day before during the lunch, was asking me about the significance of stiffness and modulus and stuff. This is where it comes into picture as well, right? Stiffness is P over delta. Modulus in this case is actually Q over delta. Q is basically, if you study like a beam on elastic foundation kind of thing, which is where a uniform pressure, a linear load kind of is applied, if you take that Q is basically U times delta. So U is equal to Q over delta. So Q technically, or sorry, U technically is not something you can calculate just by, one measurement or something. You have to have like a bowl or something. You are not, it's not a point measurement. Deflection is easy. This is a spring constant, right? You just stand something, it deflects P over K or P over delta. It's very easy. Modulus is an output of your analysis of your bowl or multiple measurements, right? So what are the influence factors? There is flexural rigidity of the rail, because now you are not directly applying load on a multi-layered elastic system. You actually have a steel. That beam is supported by some discrete supports. That beam is on an elastic foundation. First beam is the rail, second beam is the cross tie. Underneath that is your pavement, right? So your analysis changes a little bit in this case, right? So that's the flexural rigidity does affect quite a bit. Moment of inertia, cross section. For the ties, it's tie materials, concrete, wood. What is the stiffness? What is the E value? What is the I value? Because now we're talking about bending, right? EI, bending stiffness. You calculated that quite a bit in structural analysis and stuff. So that's EI. Tie spacing, depending on how far the ties are, the interaction between the rail and the tie is going to change, because the tie, very closely spaced tie, means the whole system is very stiff, right? So tie spacing, missing tie, which is basically another way to represent tie spacing. Tie condition, if the conditions are bad, if they are degraded, they are not as good in bending, stiffness and stuff. Is there any water in this thing? Yeah, that's one. That's tie condition. Then you have a hanging tie. I told you this about already. If there is contact is missing, right? Fastener stiffness, again the fastener is between the rail and the tie, that stiffness affects as well. Sublayers, subgrade layer, subgrade condition, thickness, moisture condition, ballast and subballast, ballast condition, compaction, fouling, degradation, ballast depth and everything. So all of this is going to affect your track modulus, right? This is some empirical, again, from some past work that Professor Seelig and others have done. And what they did is, if U or track modulus is less than 14 megapascal, then it's a poor track. Between 14 to 28 megapascal, it's okay. Greater than 28, it's good. So the idea is, let's just say, first of all, how does this correlate with actual response that you see in the field, right? That plus, how is this affected by, now I'm changing my ballast. Now it's a clean ballast to a fouled ballast, dry subgrade to a wet subgrade, type 1 subgrades, high plasticity clay to a low plasticity silt. All of that thing, how do they change, right? That's what this is. So how does track modulus affect? This is actually a very, very interesting plot. I want you to pay attention to this. X axis is deflection, y axis is load. Okay, imagine resistance. I'm talking about the resisting load, not the applied load, like the load due to the system supporting. When there is a train, at the very beginning, if there is a contact, loss of contact, like a hanging tie or something, then the track will go down, but there is no resisting force. So you'll have a deflection that is kind of flat. Only deflection increasing, but load is not increasing, and then it will pick up. That's what this is. Flat, and then it picks up. So this flat is the void. So if you can measure in the field the deformation of the track as a train goes or something, and then you plot the load deformation curve, you can actually calculate the voids if there is anything at the interface. And then, so if somebody assumes a linear behavior and draw a line parallel to this k, this actually, it's almost like, elastic modulus versus resilient modulus. Remember, elastic modulus happens at zero strain, but in the actual track with voids, the modulus, the mobilized modulus or stiffness actually comes after some deformation, right? So this is how the mechanics works for tracks. Okay, so how can you measure track modulus? We talked about resilient modulus, we talked about FWD. Now similar measurements but in the railroad track. How do you track modulus overall, right? What you can do is, this is pure theoretical approach. Talbot, you've heard of Talbot? Is the mechanics person, very, very famous, developed a lot of conceptual theoretical applied mechanics concept and stuff. You have multiple loads on the track, on the rail, and then you measure deflections at each point. Because u is kind of an area, if you integrate from minus infinity to infinity, it's kind of an area, right? It's a summation, many summation, it's basically area. And then you summation of p divided by summation of w, that kind of gives you an idea of your track modulus, right? How do you measure this? This is theory. How do you measure this? It's very, very difficult. Like, you have one location of loading. How do you measure multiple deflections like that, right? You have to have many sensors, or do like a imaging based work and stuff, like DIC, digital image correlation and stuff, where you do video based measurements. Then comes another approach. This is called deflection based or reduced area. What they do is they first load it with light car, like unloaded, what do you guys call it, bogie, right? The language is very different, by the way. Bogie is not a dabba in America. Bogie is basically a set of axles. So like what we say is train car bogie, it's very different. But like a rail car, that's what a car is. A bogie, a dabba is basically a rail car. So if you take a rail car, a lightly car, like not loaded or maybe half full, and you load it, and then you have like a deflection pattern, and then you fill it completely and measure another deflection pattern. The change and the summation of pH minus PL, which is basically the difference in the load, heavy minus light, and divided by the summation of the area or the difference or the deflection changes, that actually gives you an idea of the modulus. So this is another measurement approach. How can you measure? Like, in pavements it was easy, FWD, right? You just measure. Here you have to, there are many different options and different challenges. This is the mechanics based approach. This is what your software can give. Like GeoTrack, when you run the calculation, it will give you a track modulus, because it does the deflection analysis and everything. It can take an area, it can just calculate. It's pretty straightforward in there. So that's what this is. QS is equal to U times W, and then this is your beam equation, and then you solve it, and then you actually can calculate U is equal to third cubic root of K4 divided by 64 EI. So, and then track stiffness is P over W, which is at x equal to 0 and stuff. So that's the mechanics based approach. But it does not identify non-linearity. It is only a linear based. It's like P is equal to K times delta kind of an approach. It doesn't do at beginning, it's soft. As you load more, it becomes harder. The stress hardening behavior doesn't get captured. So there is a need for all of that as well. Tie on elastic foundation, it's pretty similar stuff, where you can just study the tie on on with Winkler's theory and stuff. So this is geotrack. I already showed you the concept of it. It can actually measure uh, or give you a modulus. Rail ties are linear elastic beams. Elastic stress dependent behavior can be modeled. Effect of only vertical component of wheel load. You don't have the ability to have horizontal. That's the big one. How does a rail go, folks? If you have a curve and a rail rides on it, who knows this at least? If this is a track, where is the wheel flange? Is it on the outside? Everybody knows that, right? That's good. So it does inside. So there is an inside here and there is an inside here and stuff like that. So when you travel, it actually pushes against this quite lot and stuff. So there is a huge lateral component on railroad tracks. It's very dissimilar to pavements and stuff. You have some shear. This actually is very big, and the way you characterize it, something called L over V ratio, lateral load versus vertical load ratio. And L over V is a big indicator of derailment potential. If you have really big L over V, that's bad for your track. Okay, so these geotracks and stuff, they don't have that. And loads, we are only looking at the tie locations up to 17 ties, and it's unable to simulate local variations in traction, just like any multi-layer elastic theory, right? We said in your IIT PAVE, your LSIM or your BISAR or something, you cannot measure or you cannot simulate variation within a layer. It's one property, it's one E value. So that's similar to what geotrack does, but you can do that using something like a numerical model like Abacus. This is the model. I showed you some pictures of it. So this is what we are doing and stuff. Let's take a look at this. This is pretty interesting stuff with track modulus. What changes? Concrete versus wood. Concrete is stiffer. Ties, talking timber ties like slippers. Concrete is stiffer, so that's higher modulus. Wood is lower modulus. Tie spacing, 18 inches versus 30 inches. Tie spacing, when you have closer ties, the bending stiffness increases significantly, right? It's a much better supported. So that's the reason it's higher. Fastener stiffness, look, 350 or versus 26. This is in the US units, and or kilonewton per millimeter is here. So the point is, if you increase the fastener stiffness significantly, this is different vendors providing different values and stuff. So if you change it, your track modulus does change quite a bit. Ballast in megapascals, so 20,000 psi versus 80,000 psi or 138 megapascal to 551 megapascal. Subgrade modulus, 10 ksi to 40 ksi. Subgrade, subballast. This is subgrade. Look, subgrade has a huge component because there is a lot of variation that happens. It has a big effect on track modulus. Similarly, subgrade thickness. Like now you will ask, what is subgrade thickness? Because subgrade is semi-infinite, it's an analysis, right? But at what point you are hitting bedrock? Because bedrock is going to support pretty good, right? Beam on elastic foundation. This is, you know this already. We're trying to, what we are trying to do is trying to study this. We're trying to, this is an FEM, and we have 1 tie, 2 ties, 3 ties, 4 ties, 5 ties. We're actually simulating gradually the weak zone, increasing, because we can't do that in something like geotrack right now. that weak zone is not possible. So that's studying the effect of modulus and stuff like that. That's pretty much it. On this side, I guess, let me see. Let me take a look at the program and then we'll see if I didn't cover anything. But I don't want to be unfair. This is the proposal. So let's see, what did we cover? Days kind of got mixed, but let's take a look at it. So pavement and railroad track design, philosophy, historical development, we did it. Substructure layer, their importance, mechanistic empirical framework, statistically based soil exploration, you guys did all of that. Introduction to subgrade evaluation, laboratory and field methods of subgrade evaluation, CBR, DCP, laboratory and field methods of subgrade evaluation, FWD, LWD, GeoGauge. We introduced everything. We didn't go into details of LWD. Maybe in the tutorial we can take a look. Interpretation of DCP, that's what today is. We did FWD already. Oh, by the way, did you guys collect FWD data yesterday? In the FWD demo you had one, right? Did you collect data? We did? What? Okay. Oh, old data. Well, we have played with it, so I don't want to. I was, if you had collected yesterday, I would have tried to do something. Mechanical properties, shear strength, modulus, we did that, permanent deformation, shear strength characterization, Mohr circle, failure envelope, drained versus undrained, analysis of subgrade and aggregates, shear strength data, you already did that. You did the Mohr circles and stuff. Repeated load behavior, resilient modulus, permanent deformation, resilient modulus data, you did that. Consideration of stress dependent, ILIPAVE, you have done it. Anisotropic behavior, we did it. Introduction to lab and geotrack, we did it. Right? I think we've pretty much finished everything. At least that's what I have planned. On the tutorial today, I'm still going to show you the last thing, DCP. What I'm going to do now is basically turn it over to you all, and what I want you to do is this. Go to your Menti.